actually, she's a mathematician with a little bit of Manchester heritage as well. So she did her PhD under the supervision of Gilbert Baumschlag, who, as some of you probably know, was one of the world's top combinatorial group theorists. And Gilbert himself did his PhD here in what was then the Victoria University of Manchester. Gilbert left in 1958, but he never forgot his time in Manchester. And actually, when he passed away a few years ago in 2014, he even left some money to fund a PhD studentship in mathematics in Manchester, so that the tradition might continue. But anyway, that's enough of the past. I think Delaram's talk has a great deal more to do with the future. So she's going to tell us about interactions between group theory, cybersecurity, artificial intelligence, and quantum computation. Delaram, please.
Thank you very much, Professor Mark Kambitis, for this kind introduction, and thank you all participants to join. I saw some faces of former collaborators, for example, Indira Chatterjee, so thank you very much, all of you, and thanks, Matt, for organizing everything. So I'm going to share my screen right now. All right, so as Mark pointed out, I'm going to speak about interactions among group theory, cybersecurity, quantum computations, and artificial intelligence. But before that, I would like to complete a little bit about myself, perhaps 5 minutes to tell you who I am and what have I been working on. So in a year and a half, I moved from New York to York, and I actually figured the name of New York is not after the city of York, but after the Duke of York, which is interesting. I went to all women elementary school and high school in Tehran, and I got my bachelor degree in math and computer science in Sharif University of Technology, and then went to the States and did a master both in applied math and computer science, especially in cryptography. I'm honored to go to university with Maryam Mirzakhani, who was the first and only fields medalist, woman fields medalist. As Mark pointed out, I did my PhD in pure mathematics with Gilbert Baumschlag. And I work in the interdisciplinary research, cryptography, applied algebra, data science, and quantum computation. As you saw in my background, I've been going from math to computer science, and I believe that there is no boundary. I don't want to identify myself as one specialist. I like to gain from one field and contribute to the other one. I had 7 PhD students who graduated under my supervision, 4 in mathematics and 3 in computer science. And they joined industry or academia. And so I'm very happy. And among them, I supervise many successful female scientists. I also did some entrepreneurship, in particular, a company in startup in New York to develop homomorphic encryption schemes. And I have collaborators in several countries. And I'm also very interested in improving the situation of women in mathematics and computer science. It seems the situation is still not so equal. And as such, I'm the founder of New York Women in Mathematics and Computing in New York. And I hope to do the same in York, and I'm working on it. So you see that as the title of my talk suggests, I work in several areas. So for example, in this wallpaper group that you see here, it's group theory, and how it connects to cybersecurity, quantum computations, and artificial intelligence. So there is always a connection, and there is interdisciplinary research in this area. So as you all know, cryptography is a branch of cybersecurity, and I've done some work in the following areas. For example, public key, encryption, key exchanges. Yeah, the most famous one are RSA and Diffie-Hellman, symmetric key encryption, digital signatures, multilinear maps, fully homomorphic encryption, authentication schemes, and secret sharing schemes. So for those of you who are group theorists, there are several groups that has been proposed for cryptography, and I mean, groups always been of interest of cryptography. They always use the cyclic groups or multiplicative groups and so on, mostly abelian groups and cyclic groups. However, in 1999, use of braid groups, which is a geometric object, geometric groups that has been started in 1999. And then after, there has been several groups that has been proposed, some by me and some by the others. So I'm not gonna have time to talk about everything, but some of them I go over. So one of them is polycyclic groups, which are generalization of cyclic groups, but with more complex algorithmic theory that are promising for cryptography. Then there are other classes of groups known as graph groups or right-angled arcing groups that plays a close role between algorithmic problems in graph theory and group theory for such groups. And then hyperbolic groups that we chose, which is very geometric objects in a way, arithmetic groups, nilpotent groups, angle groups, pre-nilpotent P groups, semi-group of matrices over group ring, small cancellation group, free metabelian groups. So as Mark is one of the top semi-group theorists, I would like to say that semi-groups have potential to be applied in cryptography, and the field has not been explored as much. Then there has been other classes of groups such as simple groups, linear groups, braid groups, Grigorchuk groups, automata groups, group of matrices, and Thomson groups that have been applied in cryptography. So currently the most famous public key exchanges are RSA and Diffie-Hellman, which one of them uses prime factorization and the other discrete logarithm problem, which both are broken by Shor's quantum algorithms. So the proposals in using algorithmic group theoretic problems in cryptography are several. The ones that attracted the most attention is a conjugacy search problem, but I do believe that there are so many other problems that should be explored more deeply, and there are lots of potential. As such, there is discrete logarithm problems instead of, say, ZP star or multiplicative groups in any general group that I will actually define for you. Then it's subgroup isomorphism problem. In some cases, it's NP complete, which is good. Group homomorphism problem, power conjugacy problem, geodesic length problem. I mentioned about conjugacy search problem, and then it's word decision problem, endomorphism search problem, decomposition search problem, and subgroup membership problem. Perhaps there are other problems that I haven't listed here. So we want an appropriate class of groups in which these problems are hard in some ways. And of course, there is always a discussion between whether this should be NP hard, NP complete, or generically hard, or on average hard. So these are all questions that are coming, and that the task is to show it's provable secure with the classic definition by cryptographers. So the field has lots of promises and a lot to be explored. So I mentioned about using polycyclic groups, and also mentioned about what problems could be of importance in cryptography. So with a collaborator in Spain, Conchita Martinez Perez, and my former PhD student, Jonathan Kryak, who is in Michigan right now. So we analyzed the computational complexity of an algorithm to solve the conjugacy search problem in certain family of metabillion groups. So metabillion groups are basically abelian by abelian groups. And there are many polycyclic groups in which there are metabillion. And we proved that in general, the time complexity of the conjugacy search problem for these groups is at most exponential. And we also showed that for a specific class of groups known as generalized Baum-like solitary groups, the conjugacy search problem reduces to discrete log problem. So you may say, well, you told us that you don't want to use the discrete log problem in cyclic groups, but this is just an example and how close and connected the group theory and number theory could actually benefit from each other. So in combinatorial group theory, there is a structure known as semidirect product of groups, or semigroups for the fact. And you know that when you make a Diffie-Hellman key exchange, two people want to communicate over a secure channel. They want to agree on a key to use it for future communication. And it's based on a one-way function, which is easy to compute, hard to find the inverse. So basically so we call the people Alice and Bob, and Alice chooses an element, say some power m, and sends GA, where G is public, and Bob sends GB, and everything is over public group ZP star. And then the shared common key will be GAB. So now we wonder, what if we actually multiply GA by GB, then both will get the same shared secret. The thing is that if you do that, everyone else is doing it. So now we want to use different structure known as this semi-direct product that actually does things differently. For example, here, so Alice chooses a private key M and computes G phi to power M. So what is G? G is a public group. It could be anything. And that's the question, what would be the best platform group or even semi-group? And then an element G in G, and phi and automorphism or endomorphism of G. So we consider basically the big group that we consider is G semi-direct with odd G or end G, depending on its semi-group or group. So Alice computes G phi to power M in the semi-direct product setting. You don't have to know much about it, but all I say is that it gives you such an expression, phi m minus 1g up to phi gg. And so call the first component A, and the second component would be phi m. So Alice doesn't make phi m public, because then everything will be just like discrete log problem, which is not interesting. I mean, why should we do something that already exists with more complex structures? So Alice publicized A, and Bob does similar thing. He picks a private element n and computes G phi to power n and call the first component B. So B is phi n minus 1g up to g and so on. So note that A and B are public now. So now Alice knows A, she knows B, and she knows M. So she can compute Bx times A phi M. She doesn't know X, she doesn't care, because we claim that the shared key would be the first component of this product. And we claim that this is equal to what Bob can compute. So he knows A, he knows B, and he knows N. So these are both equal, and they're equal to G phi M plus N. So basically, they kind of multiply what they compute in some ways, but the shared key would be the same, would be the first component. So there has been some proposal to suggest platform. So for example, if you consider G to be ZP star with some computation and using some basic geometric series that you can get, it would be, Diffie-Hellman is a special case of this protocol. So it's not good, but you just see that how generalized this protocol is. So with Vladimir Špirine, we suggested to use free nilpotent P group. And when I discuss about post-quantum cryptography, and I introduce you about hidden subgroup problem, this would be a natural question to see what is analyzing the hidden subgroup problem for these free nilpotent P groups. So these are basically finite groups in a way. So this is a work that I've done with Indira Chatterjee in University of Nice in France. So first of all, so this is more geometric idea that she proposed to me, and we successfully came up with this idea of a symmetric key encryption. So first of all, just a quick idea of what a subgroup distortion is. So consider a finitely generated group G and S a finite generating set. Then for every element G, the word length associated to the generating set of G is given by what you see here. We show length of G in the generating set S, which is the minimum N, such that you can write G as in the minimum way in the product of the generators. So we define the distortion of a subgroup in a group as follows. So let G be a finitely generated group. Suppose H to be a finitely generated subgroup. Then the distortion of the subgroup H in the group G is the function from N to N, such that it sends N to the maximum length of H in the generating set of H, which is T, such that the length of H in S is less than or equal to N. So let me do an example. So suppose this metabelian bombs like solitaire groups with this presentation. You have two generators A and B, and the relator is A, B, A inverse, which is B squared. So we want to use this relation that you see here. So if you take H to be generated by just one element B, so this is isomorphic to Z, is a subgroup of G finitely generated. So now you can compute this element A N B A minus N. So you can compute the length of this element in generating set of G, which is 2N plus 1. And then you can keep rewriting this element using the relator of G. And in the end, you can just peel off this, and then in the end, you get B to power 2 to power N. So the length of B to power 2 to power N in generating set of the subgroup H is 2 to power N. So the distortion of H in G is at least an exponential. So there is another problem that I need to define, and this is geodesic length problem. So given a finitely generated group G and finite generating set S, one can ask the following question. What is the complexity of the algorithm that given G in G finds the geodesic length of G in the generating set of S? So this question in general is, has not been explored much. But for example, for some classes of groups, we know that it's NP complete, for example, for free metabelian groups. However, there is a theorem that shows that for Gromov hyperbolic groups, the geodesic length problem is solvable in polynomial time. I think actually it's quadratic, if I'm not mistaken. So this is a symmetric. So this is the big idea. There should be more detailed version, more secure version, but I just want to give you a big idea. So this is a symmetric key encryption. As I said, it's joined with Indira Chatterjee. So what are the public information? So G finitely generated group is a public information, but because it's symmetric key, Alice and Bob have a shared subgroup, private shared subgroup, which is finitely generated and exponentially distorted in G. So you see that H is both known to Alice and Bob, but no one else knows that. So for example, Alice wants to send the number n to Bob. So what she does is that she chooses an element which in H, such that the length, the geodesic length of H in H is n. And since H is exponentially distorted in G, then if you compute the length of H in big group G, it's something smaller, a lot smaller. So this should be double in quality here. So call it M. So now Alice can rewrite H, this element H here, as generating set of G. So it's like going to be M of them, right? And sends this to Bob. Since Bob has the subgroup H, so he can rewrite this element in terms of generating set of H and find N here basically. And as you can see, we also need to assume that finding geodesic length is in polynomial time. So we suggest with Indira, we suggested hyperbolic group. That was the first one which was suggested, and with some other colleagues, Ramon Flores and Thomas Coberda, we suggested graph groups, and with Keyvan Mallahi, we suggested arithmetic groups, that we could find some classes of these groups that these conditions that we want holds. So the other scheme that I would like to mention is called fully homomorphic encryption scheme, which is known as FHE. So the idea, so this is extremely powerful, even nowadays with, tracing COVID patients. And so this is really powerful scheme to search or do computation or do machine learning algorithms over encrypted big data. So this is really interesting. And what is the definition? So if you have encryption function E, and say two messages A and B, you want E of A plus B to be E of A plus E of B, and you want it to be also homomorphic with respect to multiplication. So what does it help? So for example, if you want to find the value of a polynomial, if you want to compute a polynomial, using this homomorphic properties, you can basically compute this polynomial over encrypted data. So this is really powerful. So as a simple example, even for simple search, for example, you have a genome company that saves the data to some cloud. It has to be encrypted. So even for simple search, so he doesn't want to download the data, decrypt it, find what he wants to find, and then encrypt. It's expensive and it takes time. So this scheme gives this functionality to us. So in 2009, Greg Gentry at IBM came up with this genius idea to come up with the first FHE scheme. However, his scheme is very secure, but it's not really efficient. So you can actually download it from IBM, where he's actually the head of security. So we have a patent with my former student Halam and Vladimir Shpirin that basically is very secure, and it uses symmetric key. However, you know that we can always make public key encryption based on symmetric key. So here the plain text space is, so Z embedded into a ring R, which is a direct sum of several copies of ZP. And the ciphertext space S is another direct sum of several copies of ZP. And then here you have an ideal I, which is private. And S mod I gives you the plain text space. So encryption of an element U in the plain text space is encryption of U is U plus encryption of 0, where encryption of 0 belongs to the private ideal I. And for decryption, because when you mod this out, the row of I ideal goes to 0, then you can recover U. So what are the applications? So we work with computational medicine and bioinformatics group in University of Michigan. So Alex Wood was my former PhD student who's now a postdoc at Michigan. And so we found several applications, including one private naive-based classification of personal biomedical data application in cancer data analysis. However, who thought, algebra could have application in cancer research? However, this method, data is data. So if instead of breast cancer data, you can feed it with different data, of course, you have to make the algorithm a bit different. You can compute different things. And as I said, it has a lot of applications in the crisis these days for tracing patients with COVID-19 and the GDPR in Europe and UK and so on. So I mentioned to you about discrete log problem in general. So you know that discrete log problem, you have an equation beta is alpha to power x, where alpha and beta are public, and it's over ZP star, and you want to find x. And the question is that it's hard to find x with the current algorithms and so on, but it's broken by quantum algorithms. So you can define this over general groups. So you can say alpha, if it's like a vector alpha 1 to alpha r, and you have beta, you can write beta uniquely as alpha to power x, which we define as alpha 1 x1 to alpha r xr. And discrete log of beta with respect to alpha, it's basically discrete log alpha beta. So this is more general. And the interesting thing you could do is use it instead of ZP to say P groups, a group in which the order of every element is a power of P. So there is a really interesting application known as multilinear maps, in which we define it as follows. So suppose E is a map from Gn to Gt. So usually in the literature, these G and Gt are cyclic groups. And take A1 to An belong to Z. And some elements G1 to Gn belong to G. Then you have a multilinear map if E of G1 to power A to Gn to power An is going to give you E G1 to Gn to power A1 to An. So classically, this was proposed by Alice Silverberg and Dan Boneh in California. And they suggested using elliptic curve for this, and they only could talk about bilinear maps. So basically that when we talk about public key encryption or public key exchange, only two people can communicate. So if you have multilinear maps or even bilinear maps, three people can do the exchanges over public channel. So far, what is known is that there has not been any even trilinear maps which is secure. So with some colleagues in University of Salerno, Maria Tota and Antonio Tortora, we came up with using multilinear maps using P groups and in general nilpotent groups. So this is very interesting, and it can be done. And currently we are working on discrete log problem over P groups that for this case of discrete log problem for finite abelian P groups has been done, but not for the other classes. So it's like the search of the secure platform again is a big question. Okay, so let me see how long do I have, not much. So going back to quantum computation, what you need to know is that the common mistake that people do is quantum computers are not a replacement of the classical computers. It works faster for some special classes of problems, not always. So they use qubits, which are, you can compare classical bits, which are 0, 1, while qubits, you have a superpositions. Basically, you can have vectors 0, 1, depending on the dimension or how many bits or qubits you want to use. So you can have, more than 2 bits, you can have four qubits and so on. So depending on how many, it makes the dimension of the vector space larger. And you heard about Schrödinger's cat, dead cat versus a live cat. So why did I tell you this introduction? National Security Agency in the United States, after Snowden's revelation, made the announcement for search for post-quantum primitives. And right after, the National Institute of Standard and Technology in the United States made a competition worldwide, and in November 2017 was the submission deadline. So there has been several proposals worldwide, mathematicians, cryptographers around the world. So one of the most successful one that attracted a lot of attention was lattice-based primitive, multivariate primitive, that actually I'm very interested, and code-based primitives, hash-based primitives, isogeny-based, and group-based primitive that were only one submission. And that's multivariate and group-based are the ones that I'm interested, but today's talk is mostly focused on group-based primitive. So in October 2019, some scientists in London, both in Imperial College and King's College London, they came up with this preprint that actually just published in a good journal. And what they say is that I didn't completely refer the paper, but that's very interesting. They say we analyze the potential of adiabatic quantum computation, whatever that is, for attacks on lattice-based cryptography. So they basically attack the shortest vector problem that is basis of difficult problem for lattice-based cryptography. So this is interesting, and that gives me motivation by a quote by Swedish Nobel Prizes Thomas Lindholm that says, don't do what everybody else is doing. So I stick to my guns and I want to do my group-based cryptography. So how do you approach to show that a group-based primitive is actually post-quantum? So first of all, in general, NP-complete or unsolvable problems are susceptible to Shor's algorithm. I'm not claiming that NP-complete problems are the best to propose a cryptosystem hard problem based on that. I mean, they're really interesting and very intrinsic properties that you need to consider, like average case complexity or generic case complexity, that I don't have the time to say, but I'm just telling you overall ideas. Then there is an important problem known as hidden subgroup problem that I'm going to define. So you need to analyze that, because hidden subgroup problem for, say, finite abelian group or cyclic groups can be reduced to Shor's algorithm that can break the crypto system in quantum algorithm in polynomial time. And then Grover's search algorithm gives us the correct parameters. So here is a definition of hidden subgroup problem. So suppose you have a finitely generated group. Look at this picture here, G, and an efficiently computable function f from G to the finite set S here, such that f is constant and distinct on left cosets of a subgroup H of finite index. You see that H has finite index, so you can, make this like that, and you see that two elements in the same left coset goes to the same element. So it's constant, and each coset go to different element in S, so they're also distinct. So the question is, find a generating set for H. So when you have a quantum algorithm, you express your group, say, in a superposition way. And by definition, it's 1 over square root of the order of the group. And then you have the sum of these superpositions of G. Of course, they have some coefficients that in notation, they write it this way. So if you have an infinite group, you cannot divide 1 over the order of the group, right? So they're kind of obstacles, and that's an interesting question to think about. So one problem that I'm interested to think about is hidden subgroup problem for, say, P groups, when you have semidirect product of several copies of P, assuming that they are well defined and all that. I don't think I have much time. Is that right, Mark?
I think you certainly have a few minutes. Don't rush.
Okay. All right, so I will just tell you quickly about these graph groups. That is a very close connections with algorithmic problems in graph theory. And this is the joint work that we have several joint work that I didn't present it here with Thomas Coberda and Ramon Flores. So we basically analyzed and perhaps noted some problems. So for example, isomorphism problem in graph groups is equivalent to graph isomorphism problem, which by result of Babai is quasi-polynomial. However, some problems, for example, homomorphism problem, which is NP-complete for graphs, it also stays NP-complete for graph groups. I don't think I have much time to tell you some theorems and this, so I will tell you quickly about some. I think there are some data scientists waiting for me to talk a little bit about artificial intelligence and group theory and how it impacts cybersecurity. So you know that symmetry is present in all forms in the natural and biological structures, as well as man-made environments, and computational symmetry applies group theory and algebra to create algorithms that model and analyze symmetry in real world. So for example, the use of symmetric groups has been used a lot in optimizing the formulation of signal processing, machine learning algorithms, and so on. So this field has a lot to gain from each other. Artificial intelligence can apply group theory to basically formalize some of the pattern recognition algorithms and so on, among others, as well as artificial intelligence can help with solving some group theoretic problems, and as particular the ones that have been used for in cryptography. And that's one of the work that I've done, solving conjugacy problem via machine learning with Robert Haralick and Jonathan Groyek, my former PhD student. So just a couple of announcements and then I finish. So I hope that you or your students or postdocs will come to the trimester that I co-organized with some colleagues is post-quantum algebraic cryptography in Institute Henri Poincaré, September to December 2021. I hope that COVID will be resolved by then. And there are some journals that I encourage you to submit papers, and it covers a lot of areas that I address in the talk. So this shows that how Society for Industrial and Applied Mathematics considered applied algebra as something that can have tremendous amount of industrial applications. So this is a really good journal. And there is another journal which was started in 2016, and we are looking for submission for some papers in post-quantum cryptography and coding theory. So it would be great if you have something to submit. I'm grateful to the support of many agencies who supported my, my research throughout the year. And then in this situation, I think finding PhD studentship or postdoc is challenging, but if you have a good student, please contact me and I'll see how I can come up with a solution and find a way to have them. York is not as, is so beautiful, and it's not always rainy, as you could see in the picture, just show the beauty of this beautiful city. And we are hoping to have another workshop at York, so hopefully Manchester people especially could come. It's a workshop in quantum information complexity and cryptography, supported by Heilbronn Institute. And finally, if you want to get more information about post-quantum cryptography and called by NIST, I did a webinar in National Academy of Science last November, where actually I spoke with Dustin Moody, who's one of the directors at NIST. So this is the address. It's also on my website if you want to watch it. So thank you very much.
Okay, thank you very much, Delaram. I'm sure I thank you on behalf of everybody. There's always a slight uncomfortable bit here because of the difficulty of applauding in Zoom, but I enjoyed that a lot. And I can confirm, as somebody who lived in York for 7 years, that it doesn't always rain in York. In fact, it rains slightly less than in Manchester, but we'd have to get a meteorologist to confirm that. We've only got one question in the chat, which is from my colleague.
Shall I stop sharing or no?
Say again?
Shall I stop sharing my screen?
Maybe you could leave the screen up in case anybody wants you to see the slides again. So there's one question which is from my colleague Yuri Baslov. So I'll ask the question and then maybe I'll unmute Yuri if I can figure out how to do that in case he wants to follow up at all. So he says FHE fully homomorphic encryption seems inherently less secure than non-homomorphic schemes. Is this trade-off for ease of search justified?
So what particular homomorphic encryption is particularly, I mean, for example, the scheme proposed by Gentry using the spectral problem, so it's just encrypt. So for example, a lot of the classic public key encryptions, for example, the I don't know, LGML or even RSA and so on, they are homomorphic with respect to one operation or pair, for example. So so they are the same. So, and then they use it for homomorphic, not fully homomorphic. So I'm not clear about the question exactly.
Yuri, do you want to sort of follow up on that? I'm attempting to unmute you. Sorry, it's my incompetence. Go ahead, Yuri.
Right. Well, thank you. No, I obviously we're dealing with a case where we need to measure the sort of the possible potential risk here. So I admit that I haven't actually read that paper yet, but I'm just wondering how I was just wondering how secure is this proposed fully homomorphic scheme comparing to Elgamal or others. So
Elgamal is homomorphic with respect to multiplication, say, and it's
right.
secure. So our scheme here, that's what you mean, right?
Yes.
So our scheme is a symmetric key encryption. So it's, so just like the other, you know, symmetric key encryptions, they're secure against some of the attacks and so on.
Okay, well, I don't think we have any further questions right now, so I'll just thank Delaram again for a really nice talk. I'd also just like to very briefly thank Matt and Simon for their work behind the scenes to make this run as smoothly as it has. So thank you very much, and I guess we'll see everybody in the next seminar.
Thank you very much.
Hang on, Mark and Delaram. We do have one more question from Richard Webb.
Oh, sorry, we have one more question. Yeah, so Richard asks, now I'll have to close the session down again in a minute, won't I? Richard says, can you say a little bit more about group theoretic-based cryptography being safe in the large? Would that be a reference to random walks, for example?
So this is a very good question. So there are several group. So the complexity problems in for algorithmic problems in group theory has not been really discovered as much. So there are very few classes, a few people, including Mark, who has been done some interesting work in this area, as well as some generic case complexity that he actually worked on. But there are not many problems. So several problems here have not been proved to be NP complete or something, but then the same for, say, lattice-based cryptography. The underlying problem, we don't know how hard it is. It's just like, because for so many reasons, so many years, no one could do it. We just assume it's hard, and people use it, and they're actually conjecturing to being standardized among other things. So the field needs to be lots of lot of people need to work on it and work with theoretical computer scientists, cryptographers, to come up with what is really important when we address security. And the trimester we are organizing addresses this to bring people from different areas to discuss this. So my main belief is, for example, if you want to go from cyclic groups to some non-commutative groups, for example, polycyclic groups are generalization of cyclic groups with more complex algorithmic theory, while they still have some connections with algebraic number theory that's been already used and so on. Or for the case of graph groups, for example, the homomorphism problem is NP complete, and we made the authentication scheme. Or for subgroup isomorphism problem, there are some classes in which the problem is actually NP complete, or some cases is unsolvable, and so on. So this needs to be explored. I mean, it's still relatively, it's like a couple of decades that still needs further investigation, but.
Okay, thank you.
You're welcome. Thank you.
Okay, right. I will look very carefully to check there are no further questions in the chat. It does seem there are now no further questions in the chat. So thanks very much again, Delaram, and thanks to everyone else for coming. See you next time.